Hey everyone, welcome back to section 8.1. This is part 2. We're going to be talking more about geometric mean and how we can use it in an application with triangles, more specifically right triangles and similar triangles. So just as a quick reminder of what geometric mean is, remember, in order to find the geometric mean of something, if I have two numbers, for example, 7 and 2, if I want to find the geometric mean, I multiply them together to get 14, and then I take the square root of that number. So the square root of 14 would be your geometric mean. So I want to start, before we actually apply this in our triangles, just practicing identifying similar triangles, especially within one picture when you have multiple combined into one, because what you're going to have to be really paying attention to is the fact that these triangles are going to be rotated within each other. So order and similarity statements is still going to be really, really important. So this first little part says, if an altitude is drawn into the hypotenuse of a right triangle, so here's our altitude, I'm covering in blue, says then you create two more similar triangles. So basically what they're saying is when you draw in an altitude, you now have three triangles that are considered similar, not just one large triangle here. So what I'm going to do is I'm going to go ahead and write a similarity statement that relates all of these triangles, the little blue one, this red one, and then the largest one all together. So I'm going to start by, I'll name the little triangle first. So I'm going to say triangle FJG. So notice that I started from one corner, I went along the short side to the right angle, okay, and then I went up the long side and then down the hypotenuse. You want to make sure that you can identify the direction that you go, and that's going to make it a lot easier to name the other triangles. So now I'm going to do the same thing for the next triangle. So I named the small one, so now I'm going to go and do the same thing for this triangle here that I just shaded in. So I'm going to start with my short side, so G to the right angle, so triangle G to J, and then up the long side to H, so G, J, H. Okay, and then I could have drawn that, completed it down the hypotenuse. So notice I went the same direction as I did the other triangle, it's just turned and rotated. And then I'm going to do the same thing for the largest triangle, so I'll do that in red. So my largest triangle, I'm going to go short side to long side. So I'm going to start at the corner, short side is F, so triangle F to G, and then up the long side, so FGH. Now, one thing that I want to point out with your similarity statements is that notice in some of the letters they match up. So notice the J's match up here, but it doesn't match up in this one because we don't have J in this largest triangle. So yes, it's important to have your letters match up, but when you start rotating triangles and having them within each other, you're going to have some letters that don't match up, and that's okay. So what's more important is that you're going in the same direction rather than making sure every single letter is lined up exactly. So I want you guys to go ahead and try this example here. We have three triangles in this picture, the smallest, the medium, and then the largest. I want you guys to write your similarity statements and then check your answer and see how you did. Now that we are able to identify the similar triangles, hopefully that was pretty easy for you, now we're going to be using the geometric mean within these triangles. So the first part is our geometric mean theorem with the altitude. So it says that the length of the altitude, remember altitude starts at an angle and comes straight down to make a right angle, so here's our altitude, is the geometric mean between the lengths of the two segments. Okay, so notice the two segments that we're working with are along the hypotenuse of the largest triangle. So the way we could write this in terms of a formula would be that our altitude, so h, is equal to the geometric mean of the two partial segments here. So x times y, so the square root of x times y. And you could also think of this as, we're getting this from a proportion. Okay, so really what we're getting here is this part of the hypotenuse, the x, over our altitude is equal to our altitude over the other portion of our hypotenuse. And if you were to cross multiply and solve this, we get x times y, so xy, equals h squared, because h times h is h squared, and then to get h by itself we take the square root of both sides. So this is where the geometric mean is coming from and why we can just jump to this formula, okay, where we get h is the square root of xy. All right, so obviously this is much quicker to just know that it's the geometric mean and plug into your square root, but this is where it's coming from, is from this proportion, because we're still talking about similar triangles, so proportions still apply here. All right, so let's go through an example of this. Okay, so we've got this triangle here, and it says solve for x. Okay, so you can ignore z and y. In this case, we'll talk about those in a minute, but x is our altitude, so we're going to say the altitude is equal to, and then remember it's the square root of the portions of the hypotenuse. Well, we have two parts of our hypotenuse. We have this side here, so 20, and then times, and then we have the other side next to it, 5. So 5. And so now we just have to multiply. So we get x equals the square root of 100. Well, what's the square root of 100? We get 10. So our altitude in this particular problem is 10. Done. So hopefully that's not too bad. Keep in mind you could have a variable in a different place, so it may not always be the altitude that's the x. Maybe it's a part of the side or of the hypotenuse that's the x, and then you'll have to do a little bit of solving. So this is not all the examples. This is just one particular example. Now the next part of the geometric mean is when we are using the legs of the triangle. So here is our definition, more of our theorem, okay, what it says in the book. So the length of the leg of a triangle is the geometric mean between the hypotenuse and the portion of the hypotenuse that's adjacent to it. So there's a couple of things that you need to know in terms of vocab. Remember, adjacent means next to, okay, or connected to. And then also, we know that hypotenuse is always across from the right angle, so that helps us. And remember, a leg of a right triangle is a side that's not the hypotenuse. So there's actually two formulas that we're going to get out of this. Let's start with B first, just because that's the shorter leg. It doesn't really matter. Okay, so what this says is that the leg, so B, is the geometric mean of the whole hypotenuse, so C, times the leg that's adjacent to B. So that would be x. Right? So this leg is equal to the geometric mean of C times x, and then we could solve. And the same thing applies for A. So this is just the other side. So A is going to be equal to the geometric mean, so square root of the whole hypotenuse. But this time, instead of multiplying it by x, we're going to multiply it by y, because y is the portion that's next to A. So C times y. So notice it's the same formula, geometric mean, okay, but what part of the triangle we use is going to change a little bit depending on what we're solving for. So make sure you draw this picture and that you write those formulas down. So using the same example, same triangle that we were able to find in the last example, we're going to try to solve this time for y and z. So let's go ahead and start with y first. So here's the leg. So remember, the leg is equal to the square root of, we want to take the whole hypotenuse. Well, the whole hypotenuse, even though they don't give it to us, we can add these together, so we get 25. So 25. And then times the portion of the hypotenuse that's closest, so times 5. And now all we have to do is go ahead and solve this. So we can just multiply 25 times 5 and get 125. So we get y is equal to the square root of 125. And then, of course, if you can simplify this, I would definitely do that. Unless it wants decimal answers, I'd leave it in terms of square roots. So you get 5 root 5. Now, if it did want the approximate decimal answer, this one would be 11.18, and then you'd be done. So there's the y. Now we're going to do the same thing for z. So z, that's our leg, so this one right here, is equal to the square root of the whole hypotenuse, so 25 again, times this portion of the hypotenuse closest to z, so times 20. So now we can go ahead and multiply 25 times 20. That gets us the square root of 500. So we can go ahead and take the square root of that if we reduce it down, and we get 10 root 5. Now, if you're having trouble reducing radicals like this, please make sure you ask me in class, and I will gladly go through that with you. It's a really important skill to have, especially if you're getting ready to take I-STEP or anything like that. And then obviously decimal-wise, this would be 22.36 if they asked for it. All right, so it's all geometric mean. Remember, geometric mean comes from proportions. I showed you that at the beginning of the notes, how we got our square root formula. So you could always set up a proportion if you want, but jumping to this short formula hopefully will make this section pretty easy. So if you have any questions about geometric mean, let me know. Otherwise, you guys are done with this section. Thanks for listening.